Okay, so welcome back. So today we're going to start talking about exponential functions. And so the first thing that we want to discuss is how do you identify an exponential function? Well, we have to know how it behaves. Okay? So let's consider a linear function, right? A linear function is a line, a straight line. Like, for example, in this case. And so what do we know about the behavior of straight lines, linear functions? Well, linear functions have a constant slope, okay? A constant rate of change, okay? But when you talk about an exponential curve doesn't have a constant rate of change. It has a rate of change that changes, okay? So, for example, this would be an example of an exponential type curve. Or it could be, right? We have to go a little bit further, do a little bit further analysis. But something like this could have a exponential curve. Or this could have an exponential curve. Now, the distinguishing feature of an exponential curve is how the rate of change is occurring. So, in an exponential curve, instead of having a constant rate or a constant slope, we would say that the slope changes is a percent change, right? It's a percent change of what? It's a percent change of the original amount. Okay, so instead of a constant rate where it's going up at the same level, okay, the same slope, what we say here is the increase, the amount of the increase goes up by a certain ratio or percentage. So there's a percent increase or a percent decrease, okay, based on the original amount or the previous amount. So, for example, we might have something like this. F of x equals 4x plus 0, right? Or 4x plus 3. But I could also represent a function as f of x equals 2 to the x. Or I can have f of x equal 1/2 to the x, where this would all be in parentheses, okay? Or I put in parentheses just to make it clear. So now, these two are exponential curves or exponential functions, okay? And the reason why we can see that is because of the form. They have a constant ratio, 2. So then in this case here, this is telling us that y, the function, is doubling for every unit of x. So if x is 0, we have 1. If x is 1, we have 2. If x is 2, we have 4. If x is 3, we have 8, and so on. 16, 32, 64, 128, 512, and so on. Okay? So now, that's an increasing. This is what we call exponential growth. Okay, so this is what we call exponential growth. Okay. Now, if we look at this one, we see that the common ratio here is 1/2. So that means for every whole number of x, this thing is going to go down by half. So that means we're going to start with 1, then it's going to go to a half. When x is 1, it's a half. When x is 2, it's a fourth. When x is 3, it's an eighth. And then a 16th, and 1/32nd, and 1/64th, and 1/28th, or 1/128th, and so on. And so this is what we call exponential decay. This is exponential decay. So, exponential growth will look something like this. Exponential decay will look something like that. Okay? So, what else can I say? So just to reiterate, so exponential growth refers to an increase based on a constant multiplicative rate of change, or a constant ratio, over equal increments of time. Okay? So what that means is a percent increase of the original amount of time. Now, percent decay, or exponential decay, refers to a decrease based on a constant multiplicative rate of change. Again, constant ratio. Over equal increments of time. Okay, or this is what we call a percent decrease from the original amount. Okay. Okay, let's see here. Now again, we don't want to use, well, we want to be concise in our language. So but remember, we're looking at by the same percentage, right? We want increase or decrease by the same percentage. We don't want to say by the same amount. Those two phrases are significantly different. Okay, so be aware of that. What else do I want to do here? Is there anything else that I want to say? Nope, that's it. So next time we'll get into the characteristics of exponential functions, and then graphing and so on. Have a great day.